you ever wondered why you see your image in a mirror, or why a straw appears bent when placed in a glass of water? These everyday observations are fascinating examples of how light interacts with different surfaces. In this video, we'll explore the science behind these phenomena, reflection and refraction. Understanding how light behaves when it strikes various objects helps us make sense of many things we see around us. Let's begin our journey by looking at the basics of light and its behavior, setting the stage for a deeper dive into reflection and refraction. Mirrors are everywhere from bathrooms to cars, and they work because of reflection. When light hits a shiny surface like a mirror, it bounces back, allowing us to see our own image. This bouncing back of light is called reflection. It's the reason you can check your appearance or see objects behind you using a mirror. The process is simple but powerful, and it forms the basis for many optical devices. Let's look closer at how light travels and interacts with surfaces to create reflection. Light always travels in straight lines unless it encounters an obstacle or a different medium. This property is fundamental to understanding how shadows are formed and why light behaves predictably when it meets surfaces. When light falls on a shiny surface, such as a mirror, it doesn't just stop, it bounces back, creating a reflection. This straight line travel is what makes the laws of reflection so reliable and easy to observe in everyday life. Reflection is the process where light bounces off a surface. When you look into a mirror, the light from your face hits the mirror and reflects back to your eyes, allowing you to see your image. This phenomenon is not limited to mirrors, it happens with any shiny surface. Reflection is responsible for many optical effects and is a key principle in designing devices like periscopes, telescopes, and even cameras. Incident ray is the ray of light that falls onto a surface. Imagine shining a flashlight at a mirror. The beam that hits the mirror is the incident ray. This ray is the starting point for understanding how light interacts with surfaces and sets up the conditions for reflection. The incident ray's direction and angle are crucial for predicting how the light will bounce back. After the incident ray strikes the surface, it bounces back as the reflected ray. This is the ray that travels away from the surface, heading in a new direction. The reflected ray is what allows us to see images in mirrors and shiny objects. Its path depends on the angle at which the incident ray hits the surface, making the relationship between the two rays essential for understanding reflection. Normal is an imaginary line drawn perpendicular to the surface at the point where the incident ray strikes. It helps us measure angles and understand the behavior of light during reflection. By comparing the angles formed by the incident and reflected rays with the normal, we can predict how light will bounce off surfaces. The normal is a reference line that simplifies the study of optics. Angle of incidence is the angle between the incident ray and the normal. This angle determines how the light will reflect off the surface. If you change the angle at which light hits a mirror, the direction of the reflected ray changes accordingly. Understanding the angle of incidence is key to predicting the path of light after it strikes a surface. The angle of reflection is the angle between the reflected ray and the normal. According to the laws of reflection, this angle is always equal to the angle of incidence. This relationship helps us understand why mirrors create predictable images and why light behaves consistently when bouncing off surfaces. The first law of reflection states that the angle of incidence is equal to the angle of reflection. This means that the direction in which light hits a surface is mirrored in the direction it bounces back. This law is fundamental in optics and explains why images in mirrors appear as they do. Second law of reflection states that the incident ray, reflected ray, and normal all lie in the same plane. This means that all the rays and the normal are aligned in a flat, two-dimensional space. This law helps us visualize and draw diagrams of reflection, making it easier to understand and predict how light will behave. Reflection can occur in different ways depending on the surface. Smooth surfaces like mirrors produce regular reflection, creating clear images. Rough surfaces like walls cause diffused reflection, scattering light in many directions and making images unclear. Understanding these types helps us see why mirrors work so well and why walls don't show our reflection. Regular reflection happens on smooth, shiny surfaces like mirrors. The light rays bounce off in a uniform direction, creating a clear and sharp image. This is why mirrors are used for seeing our reflection and in optical instruments. The predictability of regular reflection makes it useful in many applications. Diffused reflection occurs on rough surfaces like walls or paper. The light rays scatter in many directions, so no clear image is formed. This is why you can't see your reflection in a wall. Diffused reflection helps illuminate rooms evenly as light spreads out instead of bouncing in one direction. Spherical mirrors are curved mirrors that come in two main types, concave and convex. These mirrors are used in various devices and applications, from vehicle headlights to rear-view mirrors. Their curved shape affects how they reflect light and form images, making them useful for specific purposes. Concave mirror curves inward like the inside of a spoon. It focuses light to a point, making it useful in vehicle headlights, shaving mirrors, and solar furnaces. Concave mirrors can form real or virtual images depending on the position of the object, making them versatile in optical applications. Concave mirrors are used in vehicle headlights to focus light and make it brighter. They are also found in shaving mirrors, where they magnify the image for a clearer view. Solar furnaces use concave mirrors to concentrate sunlight and generate heat. These practical uses show how the shape of a mirror can influence its function. A convex mirror curves outward like the back of a spoon. It spreads light out, providing a wider field of view. Convex mirrors are commonly used as rear-view mirrors in vehicles because they allow drivers to see more of the road and surroundings, enhancing safety. Convex mirrors are ideal for rear-view mirrors in vehicles. Their outward curve lets drivers see a larger area, reducing blind spots and improving safety. Convex mirrors are also used in stores and public places for surveillance, helping monitor wide spaces with a single mirror. Refraction is the bending of light when it passes from one medium to another, such as from air to water. This change in direction happens because light travels at different speeds in different materials. Refraction explains why objects like pencils appear bent when placed in water. When light enters a new medium, its speed changes. If it moves from air to water, it slows down and bends towards the normal. If it moves from water to air, it speeds up and bends away from the normal. This bending is what causes the refraction effect we see in everyday life. Classic example of refraction is a pencil partly dipped in water. The pencil appears bent at the surface because light rays change direction as they move from water to air. This optical illusion is a direct result of refraction and demonstrates how light behaves at boundaries between different materials. There are simple rules that describe how light bends during refraction. When light enters a denser medium, it bends towards the normal. When it moves to a rarer medium, it bends away from the normal. These rules help us predict the path of light and understand optical phenomena like lenses and prisms. When light enters a denser medium such as water from air, it slows down and bends towards the normal. This change in direction is due to the difference in speed between the two mediums. Understanding this rule is important for studying lenses and other optical devices. When light moves from a denser medium to a rarer one, like from water to air, it speeds up and bends away from the normal. This rule explains why objects underwater look different when viewed from above and is essential for understanding how light travels through different materials. The refractive index is a number that tells us how much light bends in a particular medium. It compares the speed of light in that medium to its speed in air. Materials with a higher refractive index bend light more, making them useful in lenses and optical instruments. Knowing the refractive index helps us design lenses for glasses, cameras, and microscopes. It allows scientists and engineers to predict how light will behave in different materials, ensuring clear images and accurate measurements. The refractive index is a key concept in optics. Reflection is used in many devices from mirrors in homes to periscopes in submarines. It helps us see around corners, check our appearance, and even focus light in telescopes. The principles of reflection make these tools possible and improve our daily lives. Refraction is essential in making lenses for glasses, cameras, and microscopes. It allows us to focus light and create magnified images. Refraction is also used in prisms to split light into colors, helping us understand the spectrum and study light's properties. Mirrors are a part of our everyday routine. From checking our appearance to using them in vehicles for safety, mirrors rely on the principles of reflection. Their ability to create clear images makes them indispensable in homes, offices, and public spaces. Lenses use refraction to focus light and form images. They are found in glasses, cameras, microscopes, and telescopes. By bending light, lenses help us see clearly, capture photos, and study tiny objects. Refraction is the principle behind all these optical devices. Prisms use refraction to split light into its component colors. When white light passes through a prism, it bends and separates into a rainbow. This process helps scientists study the properties of light and understand the color spectrum. Optical instruments like telescopes, microscopes, and cameras use both reflection and refraction to form images. These devices help us explore the world, from distant stars to tiny cells. Understanding light's behavior is essential for designing and using these tools. Reflection isn't just limited to mirrors. It occurs in nature too. For example, lakes and ponds reflect the sky and surrounding scenery, creating beautiful images. Reflection helps animals see predators and prey and is a key part of how light interacts with the environment. Refraction is visible in nature too. Rainbows are formed when sunlight refracts through raindrops, splitting into different colors. The shimmering effect in water and the twinkling of stars are also caused by refraction. Nature uses these principles to create stunning visual effects. Reflection and refraction are both ways light interacts with surfaces and materials. Reflection bounces light back while refraction bends it. Both processes are essential for understanding optics and are used in countless devices and natural phenomena. Modern technology relies on the principles of reflection and refraction. Fiber optics use refraction to transmit data over long distances. Lasers use reflection to focus beams. Understanding light's behavior is crucial for developing new technologies and improving communication. Mirrors play a vital role in safety. Rear view and side mirrors in vehicles help drivers see behind and beside them, reducing accidents. Convex mirrors are used in stores and public places for surveillance, making spaces safer and more secure. Light is used in communication systems such as fiber optic cables. These cables rely on refraction to transmit information quickly and efficiently. The speed and reliability of light make it ideal for modern communication networks. Scientists use reflection and refraction to study the properties of light and matter. Experiments with mirrors, lenses, and prisms reveal how light behaves and help us understand the universe. These principles are fundamental to physics and chemistry. Artists use reflection and refraction to create stunning visual effects. Mirrors, glass, and water are used to play with light, adding depth and color to artworks. Understanding light's behavior allows artists to experiment and innovate in their creations. Medical devices like endoscopes and microscopes use reflection and refraction to examine the human body. These tools help doctors diagnose and treat diseases, making light an essential part of healthcare technology. Astronomers use telescopes that rely on reflection and refraction to observe distant stars and planets. These instruments gather and focus light, allowing us to explore the universe and learn about celestial objects. Throughout this video, we've explored how light interacts with surfaces and materials through reflection and refraction. We've seen how these principles are used in mirrors, lenses, and various devices, as well as in nature and technology. Understanding light's behavior helps us appreciate the world around us and the science behind everyday phenomena. Light is a fascinating subject, and its behavior through reflection and refraction shapes much of what we see and experience. From mirrors and lenses to rainbows and fiber optics, these principles are everywhere. By understanding how light works, we gain insight into science, technology, and the beauty of the world. Keep exploring and observing light in your surroundings, it's full of wonders.